Yes. So this is the emerging chiplet supply chain panel. And let's just get the first slide. So we have 4 panelists, and each of the panelists will speak for somewhere around 5 minutes. And then we have 20 minutes that we could explore the questions and discussions. So our first speaker is Yang Li from Samsung.
Thank you. My name is Yan. I'm from Samsung Advanced Packaging team. Let me go to this one. Okay. All right, it's my honor to be here. As you can see from the graph on the lower right, as Samsung, we provided a one-stop heterogeneous integration of chiplet and a multi-HBM, right? So we know that a chiplet could come from different foundry, different node, different interconnect, different die-to-die. So we really need a one-step turnkey solution for all of us here, right? So we are happy to provide you that end-to-end one-stop solution. And then we have I-Cube-S, I means interposer, S stands for substrate. So it's a silicon interposer-based 2.5D platform. So I-Cube-E is also 2.5D, but E means embedded silicon bridge. So it's RDL-based, but it has embedded bridge. It do have potential to go bigger and also cheaper compared with the I-Cube-S. So I-Cube-R is RDL without the embedded bridge. X-Cube means true 3D, right? You can literally stack your logic die on your memory die on logic die. So do all those variations. So this graph shows pretty much the whole menu that we're going to provide. On the right-hand side is more focused on the mobile marketing. It's relatively lower cost. But left-hand side is more focused on the high-performance computing. So you can see that we, on the lower right, and that's 2.5D. In the middle is 3D. But you have lots of combination, right? You can stack your logic and logic together. That's right? And then you still use the interposer that we call 3.5D, right? So basically, you can just be innovative and then use our menu. So again, we just want to make sure that we collaborate with everybody here, and then so that we could overcome the tremendous challenges when we integrate the chiplet together, right? Yeah, so Samsung as a team, including Samsung Foundry and Samsung Memory, we actually spend lots of effort in OCP, right? So to make sure that we promote all the open computer system, right? From an advanced packaging point of view, our vision is collaborate with design, IP, EDA, OSAT, within an open ecosystem. We want to deliver advanced packaging platform to promote chiplet, and we support die-to-die protocol and chiplet development. As a summary, Samsung is promoting chiplet ecosystem and foster chiplet adoption from at least from AVP point of view. It's a packaging perspective, but I pretty sure that from Foundry and Memory, we also, as a whole team, we support the open compute platform. And then we provide a one-stop advanced packaging platform. It is a turnkey solution. We collaborate with the open source. So feel free to click the link and then to learn more about our new business unit. And then please feel free to talk to me. And then also stop by our booth in the exhibition hall. Thank you.
Thank you.
Hi. So thank you, everybody, to be here. It's a slightly different topic from what you've seen so far in this panel, because we have been very much focused on the hardware side and on chiplet side. But here I wanted to talk a bit more about the software side. You know, if you're much more agile, much more faster to build your SAP, your SoC, and it takes you 4 years now to write the software, you're not going to be in better places, basically. So we need to want to make sure that we have a coherent story when it comes to software and when it comes to managing this new entity, because, you know, when you used to have, you know, big company making their own SoC, they have control over everything they put inside, and they can put the software also at the same time. But if you want to have a market with multiple chiplet, then you will end up with a chiplet from different vendor coming with different software stack. And how do you make sure that you can manage everything in a cohesive and coherent way? So that's one of the things we're looking at inside UCIe, is like, how are we going to manage all this chiplet together, and how we can provide a standard way to do this management so that we don't have to worry about the software integration, make sure that it's easy to do and easy to achieve. And I wanted to show you first a picture of what kind of a system in the package looks like, and a very simple one with 4 chiplets. You have, you know, A, B, C, and D, and each of them has this UCIe link, which is the green boxes. And I highlight the sideband one because for management, usually we look at a sideband. We don't necessarily interested inside the main band, what we call the main band, the fast link. So every UCIe connection has a sideband link that is a low speed. Well, not that low speed, but still slower than the main band. And so every chiplet that are connected to each other, to this UCIe, for instance, they will have this sideband channel. And this sideband channel is where we're going to do the management. It's where we're going to do everything around managing the whole system and managing every chiplet individually. And all this network is now also reachable from both sides. So you can have bridges, for instance, from the outside of the chip or from inside of the chip. So, you know, some of your chiplet might be a CPU, might be some kind of an accelerator, might provide a gateway to that sideband channel. And you want to make sure that beyond management, you also have a current security story around all that, because, you know, if somebody can get on that management sideband, then there is a way that they can abuse some of the chiplet and some of your chiplet to try to attack your whole system in the package. So we're looking at all these sideband things and all this management stuff, and we're also looking at the security, and that's what we're trying to do inside UCIe, trying to come up with standard way to do management and also to look at security. And quickly on security, I wanted to point out some of the things we're looking at. It's not the full list, but I think I like some of the main topics we're looking at. So we're looking at software attack. Things like, for instance, how you can compromise the firmware, how can you use firmware bugs, and we look at how likely it is to happen, and we look at different kind of market. You know, you can have consumer devices. It's a different thing from data center, because we don't run in the same environment. We don't have the same kind of risk. And then we look at the possible mitigation we want to implement inside the recommendation for UCIe and other chiplet. And, you know, many of them are very obvious. You're going to see things like root of trust, Calyptra, secure boot to protect against a compromised firmware. When there is a firmware bug, you're also going to look at anti-rollback to protect you from somebody trying to redeploy old firmware with a bug, so that, you know, when you fix a bug, there is no way for somebody to go back to an old firmware with a bug. When it comes to physical attack, we're looking at things like, hey, how can you steal secret? You know, looking at the fuse value, how can you use the debug interface, you know, do your JTAG or whatever other debug interface you might have, because debug is also very critical for you to make sure that your chip and chiplet is working. So you still want to have it, but at the same time, it's a getaway for an attacker to attack your chip. So we want to make sure that we can protect it. You know, so we want to be able to disable debug or allow debug to be enabled with secure key and whatnot. We're looking also at glitching and stuff like that. For glitching, I only have one example here where we want to protect the bus, but obviously, like every chiplet will also have to protect its own glitch protection inside every chiplet. And last but not least, you know, we're also looking at hardware attack or things like counterfeit chiplet. You know, if somebody managed to counterfeit a chiplet, they can add something to that chiplet that will help an attacker to take advantage of the system in the package. So, you know, this is all kind of things, all kind of vector and access we're looking at inside UCIe, and so I will invite everybody to come and join us and look at all this with us and try to come up and agree upon standard definition and around management, and also looking at how we can address some of these security challenges we have when it comes to chiplet. But I want to stress, you know, all this hardware innovation is really nice, but we also need to tie up our software story and our security story together. Otherwise, it's going to be very hard to be successful inside the large ecosystem we have. Thank you so much. And I think, Matt, you next.
Hi, yeah. So I'm Matt. I'm a security architect at Nvidia, and Jérôme sort of introduced some of the things that the security work group for UCIe is looking at, and I'm going to, sort of give a more specific example of the kinds of problems you have when you go from a monolithic system to a bunch of chiplets all in the same package. So if we go back and we look at what we had with a monolithic system, right? We had a bunch of different IP blocks all in the same, all in the same piece of silicon and the same die. Functional units, compute units, memory units, and then all sort of the extra things, fuses, JTAG, debug interfaces, and we started throwing, like a root of trust in the system to start managing all these things, because as we've learned over time, right, easy access to JTAG causes all sorts of problems. It exposes a lot of inner workings of the chip, and it provides a lot of ability for attackers to go in and extract things or change behavior and make the system work in the ways that it's not intended. And so we hooked all these things up and we started providing centralized control, whether it's through fuses to disable things, whether it's through the root of trust controlling this functionality so it's only available when it's supposed to be and to whom it's supposed to be available. And because we had a single monolithic system, it was relatively straightforward to connect all these things up to this centralized control, because you have single points of access. You can control things. You can draw wires through your silicon and maintain that single point of control in your monolithic system. But as we go forward to chiplets, we lose some of that control, right? We no longer have this centralized point. Instead of having one JTAG port that gives you access to the whole piece of silicon, we've now got multiple different chiplets. All of them have their own JTAG ports because we are doing wafer test on them before they're ever packaged together. Well, whatever other kind of debug interfaces you might have, there's a lot of things you're doing to these chiplets before you've created this combined system that might have your root of trust or your centralized control. And even after you combine it, as you can see in the picture, you may or may not be hooking all of these things together, right? JTAG does allow for daisy chaining. That may not work in practice. It may be very complicated. It may slow things down too much and cause too much test time. So you may have multiple debug ports going into this package containing multiple chiplets. And so when that happens, now you start to run into a problem. If you used to have a centralized fuse that you used to just shut things down when you were done with manufacturing and you didn't want access to these things to be exposed anymore, you don't have that, right? Now we have 5 or 10 bits that we have to blow in different chiplets, and then we have to verify that they're all in the same state, right? We don't want the package to behave as if it's in the secured production mode when the memory controller is still allowing debug, right? All your memory traffic can then be exposed. And so how do you go and take where we used to have centralized control because there's either one point of access or because we could draw just straight wires to where we needed them? How do we maintain that same level of assurance in a system where we don't have those anymore, right? We don't have direct wires. We're running over shared interfaces between the chiplets. So we have to go figure out how can we tell what state all these things are in to make sure they're all aligned before we go ahead from our root of trust block and say, hey, yes, this SoC is functioning correctly. So we are going to need some kinds of standards here because it's going to be really hard to teach each individual dielet how to talk to every other dielet and collect this information in custom ways. It can be done, but you're not going to do different tape outs to work with different chiplets, right? The whole point is you can connect these things together somewhat arbitrarily. So if you don't have these standards, if you don't define what the different states and what the status bits you have to report and the controls over things like debug interfaces for when they need to be on and off, it's going to be very, very hard to connect these together and ever get your combined system into a state where you are comfortable with what it's doing. So sort of the call to action is if you want to learn more, join the UCIe security and manageability work group and help contribute to defining the standards that we can use to make all this work together. Thanks.
Thank you. Unlike the 3 speakers, I'm going to talk more about the test side, the challenges on the chiplets testing, and also some of the supply chain issues on the chiplets. Again, Tessolve is more focused in the testing side of it. We also do the design, but more on the chiplet testing, both at the ATE level, also at the wafer sort, ATE, and the SLT level. That's our expertise. So unlike the traditional normal IC or the SoC, we have the challenges is, the testing side of it, the known good die we get, and then the interconnect. So the product may use chiplets from different vendors. So you have to know what is the one chiplet to other chiplet, the communication side, and also what are the other issues that may come on the yield side and all that. So especially when it comes to DPPM. So we'll have to count which one is the one causing the issues and what causes what effects to the next level. So this is most important. And the data to be available from which chip is failing, so that like we can backtrack when it fails on the full production or the complete product. We will be able to backtrace it, which one is the causing low yields, and then can we fine tune to have the better yields or better DPPM. Again, the substrates are the most important. That defines the overall system performance. And known good die, different flows that we have. Again, integrating these different flows into the final testing is also a big challenge that traditionally what we are supposed to do versus what we are doing in the chiplets becomes much more complicated. And more, the SLT, the system level test, has become a must now for any of the chiplets. It's a must to go than you testing it on the traditional ATE. The interconnects are the ones which is mainly, you will have to know that whether all these complete package level simulations being done, all the hardware level simulations being done, that's most important in order to ensure that the complete performance is achievable on the system. And most important is, again, we used to have the guard banding that we used to do, that you have, where you have to ensure that you don't either underkill or overkill the devices by doing the either excessive testing or even something, the test coverage which is missing, so that like it will cause into a RMAs in the long run. So the interconnect testing, which used to be a slow, and now has been gone into the SSN based and then 1149.10, and which becomes much more challenging in terms of every interface that you are looking at is in the gigabits per second, and thus the hardware becomes much more challenging to achieve. So overall, where you have the wafer testing for the known good die individual dies, then it goes into the substrate 2.5D or 3D packaging. Then you get the final test at multiple temperatures. And finally, you will go through the fusing, and this becomes a complete chiplet version of it. But the other things are the substrate design and also the sockets, the thermals that is coming, the active thermal controls that are coming. So these defines the real performance, how it has to be tested. These play a very important role. The mechanical simulations for the same, and the signal integrity simulations of the complete hardware with the socket and with the ATC have to be well simulated in order to achieve the complete chiplet performance. So this drives the overall the test challenges to the next level, and thus increasing the coverage issues, and also if same thing goes into an automotive, the DPPM levels have to be even more stringent. So overall, there's a lot more challenges. But as such, the hardware and the socket and the thermal are most important in the supply chain in testing the chiplets. Thank you.
Thank you very much. And I want to thank all the four wise persons here today to answer the questions of the future of our chiplet supply chain. So any questions from the audience, please?
So when the chiplets are coming from multiple vendors, let's say from top 2-3 players, it could be either from TSMC, Samsung, Global Foundries, or at Intel. What kind of precautions and testing need to be done so that it come to the assembly line and you can have a even if you have known good chiplets, but ultimately it will not produce a known good package type. The package yield set today is a big problem. We are all facing that challenges, right? Is there any specific recommendations you guys have where people need to follow? We can actually get out of it because today the losses are quite high number, right?
Who want to answer?
Yeah, I agree. You know, it's pretty complicated, right? Especially you have multiple chiplets from multiple foundry. Some of them are technical challenges, and then to be honest, most of them are logistic challenges. So yeah, it is not easy, but we do work with customers and then customers, vendors to resolve it one by one, right? So that's why we need to work together, and then we need to have some standard, right? So, but you know, we're still working on it, right? That's why we have lots of challenge. So yeah, but that's why we are together. So, but other test expert. Yeah, you want to? Yeah.
Would you like to comment on that?
Right, yeah. So when it comes to, when you have multiple chiplets from on the package, you have to have the data from one end to other end, very stringent data. So you have to have all different combinations. What is this IC? When you call it as a known good unit of one chip causing to the other. So you have to really have the log of everything, all the history of one chip, and again, history of the second chip, history of the third, and all together, the system's history. So having this data helps so that like anything that, causing any, yield loss or any issues in later, where to go and fix it is most important. So having this data, again, as you said, each vendor is not talking to each other. That's another challenge. The chip from Intel may not be talking to AMD in the manner of what you are causing to. So this is, when you are integrating, the biggest challenge is this, how do you connect those?
I'd like to pass the comment.
No, not on hardware.
Other questions, please?
Hi.
Oh, yes. Go ahead.
Question for just the Tessolve person. The root of trust thing that was brought up, right? That's a concern. Can that be done during testing? Or
Yes.
it's already being done?
Yes, we can. I mean, again, this is, again, when you get a chip, obviously, what is it being tested for, right? What are the parameters that it has to be tested and what is the things? So again, whether it has a PCIe, DDR, there is a standard way of testing and we have that. And same when it is wafer level versus the complete product, ways of testing. So the test case will be very different when you test the at a wafer level versus at ATE level versus the complete system level. And probably the fourth one is the product level, where you have the complete software. So it becomes, you will have a much more tighter limits in the wafer sort to package and all that. Then finally, again, your 1.8 volts or 1.1 volts, it's still okay whether it becomes, 1.0 volts at the complete product level. Whereas in the wafer sort, you will really test it for 1.09 to 1.111. So that kind of a tight tolerance will be there.
So more specifically, like traceability as well as the security concerns for root of trust, can that be done during testing?
Yes, it can be.
Thanks a lot. Now, for something completely different, this is for the panel, when would you think the optical chiplets integration in this ecosystem would happen? Maybe if each of you guys could, I mean, there are people already doing that at a prototyping level, but there's, from a packaging perspective, from various elements, there's a lot of challenges, and just wanted to hear from the system and the OSAT people on the line.
That's outside my wheelhouse.
Okay. Yeah, optical definitely is coming to us. It is inevitable because you can see that in the OCP yesterday morning, everything is optical, right? So yeah, from a Samsung point of view, Samsung AVP point of view, we are looking into that. We realize that data center, HPC, AI need optical I/O. We're working on that, but ecosystem is not ready. There's some level, but yeah, we have to work together to build it up. In terms of how many years, to be honest, I think somebody today said driven by money, right? So how hungry we are, right? So if everybody wanted, then everybody invest, it will come sooner, right? But if the demand is not there yet, then it take longer.
Anybody else has a comment? Just to
Yeah.
The next question.
Yeah, I also have a question on test. Is there an expectation that you would actually run the structural test of die after packaging and final test?
Yes. We tested in both. Again, at the wafer sort, you access the complete, the IC alone. But when it comes to the chiplet, you do the interconnect level testing. Thus, both. You could still run the both. Using the interconnect, complete run, first chips, complete ATPGs, second chips, complete scan, third chips, complete scan, and so on. But as I said, you have to have the data of these three. If they can be interconnected, which is great. Otherwise, you will have to do it only individual chip-based.
Right, so those design techniques exist, so you can do the testing once it's in the package. So there would be an expectation that those test patterns would be provided by the chiplet providers. Maybe not to the integrators, but certainly to the ATE test houses. They need those.
Yes.
So we included that as a strongly recommended deliverable with chiplets.
Right.
Agree with that.
Yeah, I mean, again, it's a complete, which we have worked on some of the chiplets. The expectation is that, the complete, the scan architecture of one has to be known to the other person. Then only the integration can be smoother. Otherwise, it becomes challenging. But there are difficulties with respect to when you buy it from different vendors, they may or may not be able to share that. But at least to the I/O level, to all the interconnect, and you could be still good enough with your coverage.
I have a question.
Any other questions?
Yes. My question is more on the side of software framework that you guys talked about from Nvidia and Google. So how do you envision that there will be, say, tens of thousands of these chiplets? How will you trace all of this data? How would the future look like in terms of this test data coming together or supply chain data coming together, and what might be the opportunities there?
So I don't think you're going to trace all of the data like in total. You're going to have to funnel it down to what are the properties you actually care about when collecting these chiplets, assembling them together, testing them. On the security side, we use a lot of certificates when it comes to device identity. So I don't give you a list of every chip I've ever built. I give you a certificate for this one saying this one is authentic. I think you're probably going to have to do similar things in other domains because, just dumping all the test data for every chip ever built is not going to scale and it's not going to be practical.
I really don't have anything else to add to that. It's fully agree.
One last one. Thanks. Great panel. So for the system level test, equipment companies and maybe the chip level test equipment companies, whether it be Advantest, Teradyne, or I guess Chroma is the leading SLT. I mean, ultimately, would it be best to have one company test the chips first and then also do the whole system level thing combined?
Okay, I will do that. Sure. Thank you.